Hey, we'll go ahead and try to work through this together. There's still a lot of questions I have about it, but I can try to explain the things that I do understand. So we'll go ahead and start with the first little bit of part here. We have the structure of the heart. We have the direction of blood flow. It goes from the right atrium through into the um, right ventricle, which then gets pushed over to it goes into the pulmonary arteries, goes to the lungs, comes back through the pulmonary veins into the left atrium, um, and then it goes from the left atrium down through a tricuspid valve. I believe it's the tricuspid. It's the bicuspid valve into the left ventricle, and then up through the um, aortic semilunar valve. And that's the basic gist of it. It's very similar to the structure of skeletal muscle in the sense that it utilizes sarcomeres. The biggest difference between this is that they don't have as defined T-tubules, but they do use some ECF calcium and the contraction of the heart muscles, but mostly ICF muscle or calcium for this. Um, and they use calcium channels for this, and there's two big calcium channels. There's L type, which are the slow type of calcium channels, and then there's T type, which are much faster, and that'll come into play once we start talking about the action potentials of the ventricular muscle and the SA node. So we'll come over here. There's two types of cells when it comes to the heart and its contractile capabilities. There's autorhythmic cells, which are pacemaker cells, and then there's cardiomyocyte cells, which are contractile cells. These are the ones that are actually putting in the work and causing the heart to pump. And the autorhythmic are in charge of maintaining that heartbeat and keeping it at a regular stage. Um, Perhaps no, we'll go with autorhythmic because this is actually what causes the pulses across the heart to occur. So the autorhythmic, well, something important to note with both um, well, I guess with autorhythmic, we don't use any sodium in this process. Sodium gated channels are completely out of the picture. We instead use calcium for this for the depolarization of the cell. So we have what's called a funny channel. It's a HCN channel. It stands for hyperpolarization, a cyclic nucleotide. Um, and um, yeah, this is what's in charge of bringing us up to threshold from our base of negatives, or from our base, our resting membrane potential. So we have the funny channels start to get, there starts being inflow of that, and we reach threshold, and at the threshold, T type, just calcium gated channels go ahead and open, and they continue to depolarize us till we reach our maximum potential. At this point, we have L type calcium channels, and these L type are going to be the slower ones. And so uh, the T type occurs, it gets us up to a certain point, and then those run out of calcium in order to pump. And then our L type gets in a fight with our voltage gated potassium channels, and it balances out and plateaus a little bit up here at the top. And then eventually our L type will stop functioning as or stop producing calcium, and our potassium gated channels will hyperpolarize or will repolarize our cell back down to our resting membrane potential, and that process will start all over again. Now, when this occurs, that uh, that sends a signal throughout the rest of the heart, indicating or telling the muscles within the ventricle, within the ventricles to end up contracting. Make sure I got everything there. Sweet. Awesome. Yep, covered everything. Um, and we'll get into the polarizing of the heart and how that occurs here in a little bit, how it travels throughout the heart. But just know for now that autorhythmic leads to contractile. Now, this contractile, the heart has a resting membrane potential of around negative 90 millivolts, and that's because of how permeable the membrane of the cells are to potassium ions. So we'll have a signal uh, from the autorhythmic cells will reach this, and it will cause the outside of the membranes of the cells, the contractile cells, to become more positive. This will push uh, this will push us to threshold. After which point, once we reach threshold, voltage gated sodium channels will open, and the sodium will rush into the cell. Um, After we repolarize and we get up to this point right here, our Na or sodium gated channels will close and potassium channels will begin to open. We have a lot of different calcium channels here. Um, so we'll initially have uh, these. Um, these transient, as they call them, potassium channels, allowing potassium to lower that or begin to repolarize us. Let's see, what do these guys do here? Will eventually come down, and there'll be at this point, calcium, this ICA++ channel will open. This is a calcium L-type channel, and this will bring calcium into the cell. But at the same time, our potassium channels will continue to efflux our potassium in order to maintain a resting or a membrane potential. And so this is what we call right here a plateau of the heart. And this is actually the biggest difference between normal skeletal muscle cells and the heart muscle cells. So we'll have this plateau, and as this plateau continues in time, we'll continue to have different potassium channels open up, further repolarizing our contractile cells back to our resting membrane potential. So we have these calcium channels open the whole time, and they're bringing calcium inside the cell, but at the same time, we're pushing potassium outside the cell. As we continue, our ultra rapid potassium channels open. That'll bring us down a little bit further. Our rapid will open. That'll bring us down a little bit further. And then we have our slow, which bring us down a little bit further to the point where our inward rectifying potassium channels um, overwhelm the positive charges that are coming in from the calcium and drive our cell back down to repolarization. And that'll bring us all the way back down to 90 millivolts here. Um, and here's a representation of that there. It's very important to note. So like what I was saying earlier, that we use a lot of the ICF calcium here, but we have calcium that comes inside the cell through those L-type channels, and they cause our ryanodine channels to open up and release calcium inside, and then it acts very similarly to our skeletal muscle in the sense that it causes our myosin myosin heads to cock and then perform a power stroke, and then they go through the whole motion again. Let's see, ion channels. It's most everything. Also important to note is that there is a sodium potassium pump here, and this is pulling that potassium back inside the cell so that we can continue to use it for our repolarization steps. There's also a ATP gated potassium channel. This ATP potassium channel stays um, or stays closed when ATP is present. So in reality, it's more so like this right here. It'll stay closed so that no potassium can leave the cell through that channel. When there's no ATP present, that'll cause or allow the potassium ions to flow outside the cell. And that comes in handy whenever blood flow isn't getting to our heart and allowing us to respirate. Okay, what next? Okay, so let's go ahead and get back down to way down here. We'll walk through EK or ECG really quick. So our ECG is formed by placing a negative node above our SA node, which is kind of at the top right of our chest. It's on the right side of the heart is where that SA node will reside, and then we place a positive node um, down below our heart to the left side. And this is the flow of autorhythmic action potentials through the fibers of the heart in order to reach the left ventricle, which causes the contractile cells to contract and ultimately pump blood through the heart. And we call this lead two, is that positioning that I just described. This all functions are based on electric fields. Okay. So when we're at the SA node here, right as soon as our SA node, our autorhythmic cells begin to send out action potentials, this starts to depolarize our cell. And when, yeah, so when we're depolarizing our cell, naturally our cells are more negative on the inside and they are positive on the outside. That's how we get our resting membrane potential, the inside of our cells more negative than our outside of the cell. When our SA node sends out those action potentials, that causes the outside of the cell to become negative, which causes the inside of the cell to become positive, and then that causes action potentials to occur within the cells. So when this SA node starts to send out these action potentials, these negative signals throughout the heart, we begin to see the beginnings of a P wave right here. And how this functions is whenever these nodes pick up that there's an electrical signal being sent from negative to positive, that will cause oops, we don't want to move that. That will cause the graph to move upwards. And we can see here that as we propagate further away from the that negative node, we begin to reach a peak in our P wave right here. Um, as our atriums fill up with these negative charges, we begin to go down the septum of the heart right here. And as we approach the central point, um, we begin. This is kind of like the culmination of all those negative charges is at the AV node, and that's right here at the top of this septum. Cardiac septum, I believe, is what it's called. Actually, I'm curious, what is that called? Oh, I don't have it labeled. I'll have to look that up. Okay. But then it'll reach the AV node. And the purpose of the AV node is to then propagate those signals further. And so the SA node and the AV node work in coordination with each other in order to produce action potentials inside the ventricles of the heart. So yeah, once all the negative signals reach the AV node, this completes our P wave. And now it's the responsibility of the AV node to go and propagate these signals to the ventricles of the heart. We start a little bit below the AV node, and I believe I knew the reasoning behind that at one point, but I'm not entirely sure what it is now. But I know that the AV node sends signals right here. I don't know if that's via nerve, but it connects to the left ventricle. And as we can see here, there are signals. These negative signals are being propagated. Oh, man. They're being propagated, and we follow the average vector for these, which may seem like it's going straight this way, but it's likely going a little bit more like that there to propagate. As this occurs, we're sending negative signals towards the negative node of the heart, and this actually causes our Q wave to dip down um, on our graph. As these negative waves begin to fill up the septum here, um, we eventually get to the point where it's traveling straight down this way, and that's where we see our R wave propagate upwards. And as it goes down this way right here, it'll then start to go out like that as well, as we see here in this picture. And so we see a very large peak here with our R wave because we're getting a very strong vector going towards the positive node. We then come down here. Yeah, the SAR S. Yeah, it's labeled there. We'll label it here too. Um, our oh man, what are these called? That's right up here. That'll be easier to look at. So our cardiac muscle, our contractile muscles here are a little bit thicker on our left ventricle. And so as it's beginning to travel, so we saw it kind of coming out this way. It'll fill this area out, and then it'll have to travel back up this way. We have a general vector that's going towards our negative node, and this is causing us to get a downwards projection of our graph, giving us our S wave. It eventually fills, and we get back up here to our baseline. Let's see if we see here. And then we will begin to repolarize our cells. So the outside of the cell will become negative, or positive again. That'll start up here. Right, I believe so. Oh, yes. That'll kind of all start to go like this, back up towards the AV node. And that'll eventually cause our T wave that we see right here. A little guy right there. So overall, this is what it's going to look like here. We've got our P, Q, R, S, and T waves. And then there's also a U wave, but that one's not as or that one's not too important to talk about. Now it gets to be important when talking about there's a N stemmy and a stemmy. Uh, yes, okay. So N stemmy is depressed. We get a ST segment depression within STEMI. Now, what this means is that we have some damaged contractile cells along the um, epi or endocardium of the left ventricle of the heart. And this is because those damaged cells weren't supplied with enough oxygen via blood. And so we begin to get damaged cells here. When those cells are damaged, that makes it so that they can't regulate their um, resting membrane potential. And that makes it so that the outside of the cell always remains negative. So that affects our ST segment by keeping those charges negative and causing us to hyperpolarize and to repolarize much slower um, within those or from those cells just because they're damaged. And this causes them to have an abnormal S wave. ST segment elevations are much worse. This is whenever it's gone from endocardium cells that are damaged due to hypoxia to epicardium and even myocardium cells that become damaged. This causes all those cells there to not be able to regulate their resting membrane potential. And what happens is that instead of our regular dip, like what we would see up here with our S wave, coming down because we polarize that whole section. Instead, what happens is um, we're not able to depolarize this area, and so we end up getting um, uh, vectors moving towards the negative end. Wait, no. We end up getting vectors going towards the positive end because these are hypoxic, and that causes our ST wave to shift upwards and disallows these disallows the S wave to dip down as far as it normally would. Let's see, what am I missing on that? Yeah, okay, we'll jump into the effects of norepinephrine and acetylcholine on the heart. I'll try to make this pretty quick. Hopefully you can hear me as well. Maybe that's better. Um, so our autoarrhythmic cells are affected by the actions of catecholamines as well as acetylcholine. Um, I believe catecholamines. Let's see. Okay. Yeah, so catecholamines such as norepinephrine, which contribute to our adrenal gland, um, can affect our autorhythmic cells. So when we have, for example, norepinephrine come over to our beta 1 receptor, which is part of our adrenal system, or the SNS um, system of our heart, this will then increase our uh, adenyl cyclase. This will increase CAMP and cause our sodium channels to influx our CAMP through our funny channels. This will cause the steepness of our slope or increase the steepness of our slope or the decay of the membrane potential, which will increase our heart rate. So these funny channels will act quicker, and then that will also cause that'll cause our funny channels to move more like this, which will cause our algorithmic cells to fire quicker, as this is a rather slow portion right here for that to occur. And then that'll increase our heart rate. What is PK? So, also with adenylate cyclase being raised, that'll cause our pKa to rise, which will cause our calcium influx to increase, which will then cause the steepness of our slope right here to increase, which will cause our heart rate to go faster. It can also make our threshold more negative, so it can move this line right here further down, which makes it so that we can reach threshold quicker with those funny channels. Now, acetylcholine, which acts on our PMS system of our heart, will interact with M2 receptors, and that'll cause our beta gamma heterodimers to open up GERK channels, which will activate those rectifying K plus channels. And then that'll cause our membrane potential to become more negative, thus causing our heart rate to go down because we don't get as many autorhythmic action potentials. Um, yeah, so this channel here will cause more potassium to leave. It'll also cause our alpha subunit to break down or decrease our camp, which then flattens our slope of the funny channels. So here, it'll make the slope a little bit flatter, and that will decrease our heart rate. Our alpha subunit will also decrease camp, which will drive down or make our threshold more positive, which will also decrease our heart rate. On contractile cells, when norepinephrine hits the beta 1 receptors on there, that'll activate alpha subunits. And then this takes several different routes. Um, this will cause adenyl cyclase to increase, it'll cause CAMP to increase, and that'll cause our protein kinase A to increase. Now, this will phosphorylate four different things here. It'll phosphorylate L-type calcium channels or adenosine receptors, phospholamidine, and troponin. Each of these causing um, our, well, how do you word this? Each of these ultimately causing our heart to contract faster um, and be more susceptible to contraction. Some key things to point out here is that when our alpha subunit is activated, This will cause the interaction of alpha subunit with our L-type channels to increase, which increases the probability of calcium 2 channels to occur. So our alpha subunit will interact with L-type calcium channels. It'll also eventually, through protein kinase A, cause the phosphorylation of those channels, which ultimately increases the inotropic effect, meaning that the heart is more likely to contract. We also have here um, our lucitropy, which accelerates calcium reuptake into the sarcoplasmic reticulum. And our inotropic effect with the contractility, this enhances our calcium influx by our beta 1 receptors. So that is inotropy and lucitropy covered there. Okay, I think we covered that. Oh, and this part down here. Okay, where's that? Okay, sweet. So we're looking at pressure over time right here. And we have three lines present. We have the aorta, which is the green, the ventricular ventricle, which is red down here, and then we have our atrium, which is blue. Now, we come through here, and our ventricle. Let's see, do I have more notes on that? I don't believe so. Okay. So this initial bump right here is increase in pressure due to our bicuspid valve opening, causing um, blood to rush into or to fill the ventricle. Our bicuspid valve will then shut, causing pressure to remain equal on both sides. Once our um, ventricle shut or our bicuspid valve shuts, our heart will begin those contractile cells in the left atrium will begin to contract, causing an increase in pressure inside the ventricle. Um, and this also causes our so bicuspid valve closes, and then the ventricle begins to contract. At the same time, the semilunar valve is open. This causes, oh no, excuse me, it begins to contract to a point where the semilunar valve opens, at which point the blood begins to flow into the aorta, but the ventricle is still contracting, and so the aortic and the ventricular pressure are going up. We get to the point where the semilunar valve, or where we start to decrease in pressure because there's not so much blood to actually pump um, from the ventricle, and we reach the point where our semilunar valve closes, and our left ventricle pressure then begins to decrease. Our bicuspid valve will then reopen, and the process will start all over again. This little bump here is called the dicrotic notch, where the semilunar valve closes. And this little bump is here because blood going into the aorta through the semilunar valve tries to go back through the semilunar valve, as it's closing. Um, and so this actually causes it's kind of like a rubber band where it dips inwards, which causes pressure to decrease within the aorta slightly. Oh, and then when I go over that, okay, the last little bit, and I'll go over this. I don't really understand this one super well, but this shows our pressure to volume ratio within the left ventricle. So this black box right here represents um, the volume to pressure ratio, and this is a cyclic process. So um, as our volume increases, um, volume increases inside of our left ventricle, at which point it'll eventually contract, and we'll follow this path right up here. We'll get to the point where our semilunar valve opens, allowing pressure to move or allowing volume to flow out of the ventricle, but pressure remains constant because the ventricle is still contracting. At which point we hear the heart's semilunar valve close, and the volume of blood within the ventricle is much lower at this point, and those cells, the contractile cells, begin to relax, and then that pressure drops down again as that ventricle begins to relax and expand its volume. Um, and so it drops quite drastically. We have so um, This downward slope here is considered our end systolic volume. Our systolic volume is basically the volume during contraction, and our diastolic volume is the volume after contraction. So after everything's been said and done, I believe. Yes, we'll go with that. Now, when you subtract our end systolic volume from our end diastolic volume, we get what's called our stroke volume. So, how much blood is actually being pumped during the contraction phase or portion? And this stroke volume can then go on. We can uh, edit that, and or not edit it, but we can monitor that and see how much blood the heart is actually pumping. And certain things will affect our inotropic line, which our inotropic line. Um, well, there's several things. There's preload, there's afterload, there's that inotropic line, and all of these things can affect our stroke volume. And the stroke volume is really important to focus on whenever with patients. Thank you. Uh, Definitely, I'm going to be going to tutoring, but thanks for listening.